Manny Pimenta. Manny has been a space settlement advocate for over 20 years. He is founder and CEO of Virtual Moon. Virtual Moon's mission is to create the most advanced, accurate, and realistic VR simulation of the moon so that everyone can experience being on the moon. I think that's pretty awesome myself. His first attempt at this was 16 years ago, and it resulted in the world's first fully immersive interactive VR moon simulation called Lunar Explorer. There are many features and plans for Virtual Moon. Today, he will discuss the building of the first large-scale permanent lunar city called Saline, which will be one of the main features of the Virtual Moon. Manny, thanks. We're almost done with our day. We're almost done with our event. So, thanks for coming on board and help us kind of see the future. Thanks a lot.
Thank you. Can you hear me?
Good. Sound check, you're good.
Okay, great. Thank you very much for the invitation. I'm really looking forward to addressing the conference again. It was a pleasure doing it last year, so this is my second year in a row. And this is sort of a continuation of that presentation. So without further ado, by the way, great to see you again after all these years as well.
Thank you.
I will get to my slides. All right. So, thank you everyone again. The presentation is about building Saline with a 100,000 ton mass budget. Some of you were here last year, may remember my presentation. It was a Malapert city, a bold vision of what is possible. And the first slide shows a view of Malapert Mountain, which is the site where Saline will be built. By the way, Saline is a new name for Malapert City. Malapert City just sounded too utilitarian and completely unromantic, so we renamed it Saline. So we're southeast of Malapert, looking northward, and that's the view of the Earth from that location. This screenshot is from Virtual Moon, an early development of the South Pole region by Virtual Moon. Okay, and again, if you were here last year, you might remember this diagram. This is an early concept of Saline. It's basically a large horizontal tunnel that intersects a wide cylinder in the middle that we call the central atrium. The entire structure is built underground, but there is a surface observation dome, which is critical. One of the reasons that it's important is because we see Saline as primary function as a tourist destination, as a resort city. And so, giving people the ability to experience viewing the Earth is important. So the surface observation dome is a key feature. So these are the primary features and requirements. That it should be built on the ground, that it should have a normal atmospheric pressure and composition. So we want the environment to be as comfortable for human beings and as close to what they're familiar with as possible. It has to be built with current and near-term technology only. It's a permanent installation, so obviously you can't design something that lasts forever. So we thought 200 years is a practical, fits a practical definition of permanence. And it has to be operational by 2045. Saline basically answers the question of what could we build if financial restrictions were taken away, political factors and all of that. If the only limiting factor was technology, what could we build? And so the final design for Saline, the primary requirement is that it has to be buildable. Sorry, I keep jumping into that. So we said it's built completely underground, but we don't want it to look, for the people that visit Saline, we don't want them to feel like they're living in a cave. So inside we want to create an exceptionally beautiful environment, again, that's familiar to humans, that's connects them back to their origin on planet Earth, and basically brings the most beautiful elements of Earth and showcases them on the moon. So these are not shots of the interior of Saline. These are pictures that I collected from the internet that sort of give you an impression of the kind of ambience, the kind of atmosphere we want to create. It's light and airy and lots of light. It doesn't even have to have overhead panels or glass ceiling or anything like that. Because we can cover the ceiling with display film, and now we have completely flexible displays so we can tile the entire ceiling with a display that can actually mimic the sky. So even though you're inside the tunnel, it can feel like you're completely outdoors. So again, this is just intended to give you a sense of the kind of atmosphere we're trying to create. So I started conceptualizing Saline 20 years ago, but even back then, I had no idea how it could possibly be built, and I couldn't even imagine something like Starship would come along. As many people have mentioned, this is the game changer. Starship makes Saline possible, and that's what we're going to get into some of the details about how we see that happening. So, this is a launch of a Starship. It reaches orbit, gets refueled in orbit. After it gets refueled, it goes on its translunar flight, gets captured by the lunar gravity, and lands on the moon and delivers its payload, 100 tons per flight delivered to the surface of the moon. So remember that the concept here is that Saline must be designed in such a way that's buildable. So for it to be buildable, it has to meet some measure of reasonability. So the way that we arrived at 100,000 tons is that we will limit the supplies that will be sent to the moon to 1,000 flights of Starship. So 1,000 landings of Starship payloads on the moon. Okay, so how do we do that? We put in an order for SpaceX for 100 Starships. We assume that we can reuse the Starships 10 times each, and we load them up and send them to the moon. In this slide, you have 1,000 Starships headed for the moon. Obviously, they're not going to go in groups like this. They'll go maybe 3 or 4 per week and return, reload, and go back. And with these flights, we want to do a quick pass to see just what would it take to build Saline. So this is a simple diagram of what Saline would look like, showing the rough dimensions. It's basically a 1 kilometer tunnel that's 10 meters high by 50 meters wide. The central atrium is 50 meters high by 250 meters in diameter, the observation dome that you see there. And so this shape, general shape, results in a total volume of 3 million cubic meters and an internal surface area of 200,000 square meters. So those are just some starting numbers there. And by the way, these are all rounded up to make the figures easy to remember. So I sat down and started thinking about what would be required to build Saline and started adding up the masses, right? So the first thing that'll happen is we'll land a bunch of robots, many robots, and they'll start excavating the site. After the site excavation is completed, we want to install some kind of a pressure envelope. In this case, I would like to use graphene. We can produce graphene already. The expectation is that in 25 years, by 2045, we should be able to produce graphene in industrial quantities and have that material available to build our pressure envelope. So it will take 187 tons of graphene to encapsulate the entire internal volume with 1 millimeter graphene membrane. And because graphene is 200 times stronger than steel, it's equivalent to a 200 millimeter steel casing around the entire volume. We talked about the robots. So for the robots, we have allocated 5,000 tons. This allows us to put 25,000 robots on the moon. So everything will be a robot. If you need a crane, the crane is a robot. If you need an excavator, it's a robot. If you need a massive truck to carry materials around, the truck is a robot. So with this budget, we're just predicting or projecting 50 ton class robots. Again, these could be cranes or high capacity trucks or whatever is needed. So we haven't gotten down to the level of detail where we're identifying all the robots. Again, this is just a mass budget study. 100 robots of 10-ton class, plus a whole range of categories in different weight ranges, down to 3,000 robots at 20 kilograms each and 10,000 robots at 2 kilograms each. And so that's a total mass of 5,000 tons. I'm very partial to nuclear power. I think we already have small modular nuclear reactors. It's a matter of perfecting the technology and improving it so that we can make it usable on the moon. It's very reliable power, it's modular, it's compact, and it can be quickly installed, and we don't want to be power limited. So that's the thing. We want to make sure that we have all the power that we need to do anything that we want. If you have sufficient power, you can do anything. So that's 90 tons. So that's basically one landing of the payload, which is 100 tons. We can land three nuclear generators and have all the power that we need. Then we'd want some ISRU material processing plants. So here we're projecting 10 each for oxygen generation, for manufacturing steel, glass, sintered bricks, and other miscellaneous materials that we want to use on the moon. That will greatly cut down on the amount of material that we'd have to send from the Earth. We also want to send some raw materials. This is a miscellaneous category. I'm not sure exactly what we're going to need, but fertilizer, chlorine, and chemicals and things that we don't want to, that we want to manufacture on Earth and send ready to use on the moon. Vegetation, you saw the pictures that I showed you. So creating a verdant and really beautiful natural environment is very important. We've allocated quite a lot of mass budget for this. I'm just making a note here. A 50-foot pine tree weighs 1 ton. So we can imagine with 10,000 tons, we could basically have 10,000 trees. Obviously, that's a lot of trees. We're not going to have that many, but in addition to trees, there will be a lot of other vegetation. The thing is, all the vegetation that's not a tree can be sent while it's still a seedling or very small and allowed to grow on the moon. So the mass impact of all vegetation except for fully grown trees is negligible. In order to grow vegetation and trees, we need soil. Again, we're being very generous here. You see this is actually the greatest mass allocation. And with this amount of soil, we could cover the entire floor of Saline with an average of almost 0.5 meter of earth soil. And this is on the assumption that, of course, we won't be able to use regolith or any regolith-derived material as the growth medium. So we'll just take soil from the earth. Now, water. There's been many comments about the importance of water on the moon. I never thought that water was really that critical. I figured that if we were seriously operating on the lunar surface on a large scale, then the reliable transportation problem and the affordable, reliable transportation problem from Earth to the moon would have been solved. So the value of water on the moon is not that critical anymore. But we can leverage that. So to make 90,000 cubic meters of water, basically we would ship 11,000 tons of hydrogen, and we would derive the oxygen from these ISRU O2 plants, manufacturing plants from the surface, and extract it directly from the regolith using like a molten salt electrolysis process or something like that. So 90,000 cubic meters of water is a lot of water. It's 35 Olympic-sized pools. So it's a kilometer-long tunnel. It's 50 meters wide. So basically, you could have 2 meters of water on the entire floor of Saline could be 2 meters of water deep. That's a lot of water. We probably don't need that much, but just to show you, sorry about that, just to show you that it's easily done within the mass budget that we're looking at. We also need building materials for inside of Saline to create structures inside of Saline. So because of the different percentages of alloys that we need to combine in order to create steel that are listed here, carbon, chromium, tungsten, and so on, it's basically a 4-to-1 ratio. So if we ship 12,000 tons of these materials to the moon, we can make 50,000 tons of steel. Now the Eiffel Tower has 7.3 tons of iron, so we can make 7 Eiffel Towers with that much steel. I think that would be enough to satisfy any space architect that we have enough steel for structures inside Saline. And then we have life support modules and equipment. Again, we're thinking in terms of the design of Saline. The technical design will be all modular. So we're thinking 50 units each for air recycling, water recycling, waste recycling, each unit weighing 20 tons, plus a whole bunch of maintenance robots. So we're expecting that robotics will be advanced to the point where robots are even more dexterous than human beings, and they can do everything that human beings can do, but faster, better, stronger. And that's, I don't think that's a far-fetched expectation. Then we also allocating 1,000 tons to send multiple types of vehicles to the surface of the moon for surface transport and so on. Internal furnishings, textiles, paints, pigments, whatever you need to refurbish the full interior of Saline. Sorry, this keeps happening. Some mass allocation for 3D printers to create parts, tools, structures. You know, there's even new technology using food printers to create synthesized sort of meat and protein products, which are much more efficient to produce on the moon than to grow full-grown animals as a food source. So, so basically, we take 1,000 starships, we fill them up, and at the end, the total mass budget is 96,000 tons, which is under the 100,000 ton requirement. We still have some headroom. And like we saw in these figures above, we're being very generous with some things that we think are important, and we could cut back on those. So it looks like at first pass, this is very doable. So what do we do? Do we load 1,000 starships, send them to the moon, bring them back, reload them, and send them back to the moon again and do that 10 times each? We don't have to do that. And actually, that's not the smart way to do it. It turns out that Starship is is a very configurable technology, and it's also very modular. These are just some concepts of the types of different Starship configurations that can be manufactured. So let's take, for example, what we want to do is we want to create Starships optimized for each phase of the transportation. So, for example, the Starship that's designed to return to Earth uses sea level Raptor engines. And if we decide that we're going to create a Starship to lift material from Earth to low Earth orbit, but then create another Starship just to operate in space, then these sea level Raptor engines can go away. So that's 2 tons each engine. So that's, in this example, we would save 4 tons or add an additional 4 tons of capacity to payload capacity. We also could do away with the flaps and so on. So we can optimize the design for space operations. And so we could transport the material to low Earth orbit and then place the payloads on a space optimized vehicle. One approach might be to design a vehicle where the entire payload section just detaches, and then we can attach all the payload containers and attach them to a strut or a structure of some type, and attach propulsion units to that strut and create something that looks like this. This is just a quick conceptual drawing of what this would look like. So these are 6 full 100-ton Starship payloads, and these are 3 propulsion modules that would use to transport these from low Earth orbit onwards, and these would be optimized. So we would gain a lot of efficiencies and reduce the cost of not the cost of fuel, but the amount of fuel needed to transport the payloads for the next leg. So this is just a quick diagram of the delta V distances between the different locations. So here you have 6 payloads delivered to Earth orbit, and we would load them on a specially designed transport, a space tug or a space barge. You could think of it that way. And that would transport it to the next stage. I'm thinking L1 would make a good staging location. And then we would design a special design system, again, using propulsion modules and engines and so on from this Starship design. And those would take it the rest of the way to the surface of the moon. So with that approach, building something like this, it really sounds possible. And we could do it with 1,000 flights, 1,000 Starship payloads or less. Now, some of the key technologies, power generation, we talked about modular nuclear reactors. Those, I think those can be considered that will be fully matured in the next 20 years. Thermal management technologies, those don't seem to be a problem either. Life support systems. Of course, there are life support systems for space already. The challenge here is we want to create life support systems that are 100% fully closed cycle, or as close to it as we can. So that would be the challenge. But again, we have 25 years to perfect these systems. I think that's plenty. Robotics, we talked about that already. Other technologies that are going to come into play and are going to be very important: artificial intelligence, quantum computers, graphene and other manufactured materials, engineered materials, ISRU, and dust mitigation. Now, just a quick comment on dust mitigation. Dust is going to be very difficult to deal with. One of the things that we can do to mitigate against the dangers of dust or the degradation to equipment performance and duration is we could just do away with wheels. If we just have articulated robots with articulated legs as like insects, then those can be covered with some sort of fabric and material. And as long as you don't have rotating parts, the covers, the coveralls, you think of them as coveralls, will protect the entire mechanism. So Saline is being built as part of Virtual Moon. We actually have a sort of a breakout section of Virtual Moon called Virtual Moon Under Construction. Here we are creating some rapid prototyping for a few demonstration projects. We already have an Apollo 11 site and a South Pole site. The Saline construction site is already in development, and next year, if I can present again at this conference, I will have, I will be able to report on the progress on that. But before we get to Saline in 2045, we want to get there in virtual reality. So there'll be a virtual reality simulation of Saline with all the features that we talked about. And we're going one step beyond. It's not just going to be a visual simulation, it'll actually be a digital twin of the engineering design of Saline. So with that, I'll wrap up and take any questions if there are any. Thank you.
Thanks a lot. I'm really, really interested in the VR topic. And James Burks posts Saline in VR, exclamation point, awesome, exclamation point. So are you know, not to just to jump away from Saline, but can you talk about a little bit more about the VR stuff?
Sure. So Virtual Moon is the follow-on to Lunar Explorer. Lunar Explorer was the world's first complete simulation of the moon. We simulated the entire surface of the moon using Clementine data, and we created simulations of all the Apollo landing sites, all the Soviet sites, and the surveyor sites. So you can go and visit those sites, walk around among the equipment, and you know, click on pieces of equipment and learn about the science experiments done and the information that we found out about the moon. But and this was a fully immersive, interactive virtual reality simulation 16 years ago. But 16 years ago, there was no virtual reality hardware that consumers had access to, and now we have it. Yeah. So and so Virtual Moon is sort of the new reincarnation of Lunar Explorer for the new virtual reality hardware.
Cool.
But it's also based on LRO topology, which is much higher resolution than the Clementine, and also takes advantage of the new virtual reality technology. So it'll be a massively improved version of that.
That is really cool. We have to move on to our next guest, who just posted a question. Is the virtual simulation available in Oculus? If so, is there a link?
Yes. You can email me or visit our Virtual Moon website, virtualmoon.space, and register. We have a place where you can enter your email, and I'll send you a link. You can actually experience Apollo 11 right now in virtual reality using Oculus.
Neat. All right, and there's another question. Is it? I'm going to guess this is. Is there enough of a physics engine that objects react in 1/6 gravity?
That will definitely be part of it. We're going to not simulate the moon. We're going to create a digital twin of the moon with all of the environmental properties of the moon and physical properties.
Amazing. All right, we got to move on to our last speaker. Thank you very much, Manny. It is great to see you again. It's been a long time.